Well, hello class. Here's a video solution to number 24. And I'm really glad somebody asked this one because it I think it's one of the harder things to do in this particular relativity one is the addition of velocities. Now, number 24 is probably a little bit easier than the next question that was asked, and so I'll follow that up in a moment. Number 52. But both involve what we call the addition of velocities. That is, what is the velocity of something as seen by another observer? Watch, let me kind of explain, and I'll start with a little background here because at first this looks like a complicated equation, and it is kind of complicated, but I think you need to understand kind of the background. So forgetting relativity for a moment, let's just say the following takes place. Let's say there is a baseball flying through the air for whatever reason. Maybe this is a pitcher or something. And so some pitcher throws this baseball, and just for the sake of discussion, let's say they throw it at 80 miles per hour, just using non science units here, but using the English system. But if that baseball is at 80 miles an hour, you have to stop and say, wait, 80 miles relative to whom? See, in other words, maybe that's relative to some batter. Maybe the batter is standing over here, and so they're stationary relative to the earth as they are throwing the baseball. And so what you're saying is really the distance is closing at 80 miles per hour if it traveled a whole hour. But let's just say, again, for the sake of discussion, there was, how about the pitcher on this side? And the pitcher who threw the ball is, of course, stepping forward as they wind up and they throw it. And so the pitcher, in order, to get this high rate of speed, is in the process of moving this direction. And again, for the sake of discussion, let's just say, the pitcher is moving towards the batter, and I'll just say, they go at 20 miles per hour as they push off the rubber as hard as they can. But I hope this is obvious then. If you were to ask then, at what rate is the baseball traveling relative to the pitcher, you're asking then at what distance the spreading between the baseball and the pitcher. And I think you would then say, well, that's pretty obvious. That's only 60 miles per hour. Because what would happen is, this baseball relative to the ground is going to travel 80 miles in 1 hour if it went for a whole hour. But the pitcher would travel 20 miles in that same 1 hour. And so the gap between the pitcher and the baseball is only 60 miles. So therefore, the speed is 60 miles per hour. And I don't think there's much really enlightenment about all this, only here to point out then that what's absolutely crucial and has nothing to do with relativity here is that the speed of something, the speed of this baseball then is coupled with as seen by whom? Speed relative to whom? Because if there was then on the side here, say somebody driving in a car, and then you ask, okay, what speed is this baseball as seen by the person in the car? And let's say the car is moving along at say 70 miles per hour. Again, you would say then the gap is opening up, and you would say, this baseball would be 10 miles in front of the car after an hour, so it's only 10 miles per hour. But all of this is to say that the speed of something has to be coupled with the phrase relative to whom. And so that, again, I don't think is a big enlightenment, but it does then bring up this issue. And I hope I didn't make it too complicated by bringing kind of a third person into there. So let me cross off the third person and say, okay, there is then one object and two different observers. And there is a mathematical connection between these. And so we have this complicated formula for relativity, which I haven't got into, which is much more complicated than just adding distances. This is the whole weird thing about relativity and what is often referred to as the 30 years that shocked physics. It's more complicated than just adding distances. So I'm going to get to this problem number 24 in a second, I promise. But I just wanted you to see that nothing about the speed being relative to some other observer is actually new in this chapter. We've been doing it for a long time here. And each of these people would then say the speed is different. It's relative to whom. It would be very similar to driving a car, looking at another car versus somebody else in yet another car looking at it. And so your three objects then, two people in a car looking at a third car. And maybe that's not a good analogy because I got too many cars that you're going to confuse this. But the point is there's an object and then there's two people looking at it. And that's what I'm trying to say here. So we should then have some symbolism, and there would be three velocities. There would be the velocity as seen by one person. We call that u. There's the velocity seen by another person. We call that the u prime. And then there is the velocity between the two people who are watching them. And there's a mathematical connection between these three. And that's where I really want to begin this problem, because we have a nice little formula that was derived. Let me not derive it here. I did it in the lecture. Your book does it. But it simply states here that if you wanted to calculate then the velocity, we've got this u prime, so the speed seen by one person is equal to the speed seen by the other person minus the velocity between the two. And that's how we would have done it before the relativity. But now there is this extra factor down here that has to do with the time dilation and length contraction, and also is the mathematical piece that will never, ever, ever, ever let this object appear to go faster than the speed of light from any observer. Or, put another way, this same formula, if this object is already going the speed of light as seen by one observer, it will also always be seen as going the speed of light from the other observer. And so this is the amazing discovery by Einstein. Now we could go the other way around and say u is equal, and then we would have the u prime plus the v over 1 plus u v over c squared. But there's two real important things that I want to point out before I actually dive into this problem, and that is, what do each of these symbols mean, okay? And so I'll say it again. The u is the velocity as seen by one person, let's just say the batter. And so in this case, the u would be the 80. The other u, that's why they have the same symbol, but it's with a prime, and don't think that means a derivative. They're just trying to say a different speed. This would be the speed as seen by the other observer, so let's say the pitcher, okay? And then the u is the speed between those two, and so there's a mathematical formula connecting these. So you could use either one of these or both of these. And by the way, the other big thing I want to point out, did you notice that I said u is the speed as one observer? It doesn't matter which one you assign to. We could say u is the speed of the pitcher, sees the ball, or we could say u is the speed that the pit. Oh, I'm sorry, I said that. U is the speed that the batter sees the ball moving, or we could say u is the speed that the pitcher sees. There is no uniqueness about this. That's part of the whole point of relativity. There is no one frame that is more significant, important than the other. And so sometimes I have found students really struggling with that, going, well, which one is the u and which one is the prime? And I'm going to hopefully make it easy for you. It does not matter. Just pick one. So we often like to put like a little grid here and call this the normal grid, XY. And then this other one, well, we like to call it the prime grid, so X prime and Y prime. So once we choose the prime system, what we're saying is this is the speed as seen by the person in the prime system. And then the u is the speed as seen by the person in the unprimed system. But there's nothing special about that. We could take away the primes, and this then would be now the speed as seen by the unprimed system, which would now be the pitcher instead of the batter. And then, of course, if we do that, then this has to be the prime system. And so now the u prime becomes the 80, and the u now becomes the 60. And so there is no right or wrong choice about the prime and the unprimed system. So know that you don't need to struggle with that. And I know in the past students have really struggled with that. And that's why, again, probably making this problem way too long, because this is what students tend to struggle with. The only thing you need to remember is these u's are the speed of the object as seen by the other two observers, and then v is the speed of the two, and now as seen by the unprimed system. And it's important we say from the unprimed system, because when you switch these, the magnitude's the same, but the direction is different. For example, if we call this the unprimed system, the batter, then the pitcher is moving in the positive direction at 20. But if we were to call this the unprimed system, from the pitcher's point of view, the batter is moving towards the pitcher at a speed of 20, and it would be a negative 20. So it is important we understand what v is. V is the velocity of the primed system as seen from the unprimed system, and so there could be a plus or minus. Okay, but again, notice then I can use either one of these formulas. And of course, if I'm trying to find u, I like to use this formula. Oops, I forgot a prime there. And then if I'm using the other formula, this one here, or if I'm trying to find u prime, I like to do this one, because this one's already solved for u prime, and this one's already solved for u. Now, if I'm trying to figure out what v is, each one of these is about equivalent, so it doesn't matter which really one, and it's kind of hard to go through all the math to get the v, so those are the harder problems. But I hope in that long discussion, and whoops, I'm already 13 minutes into this solution, and really am more lecturing than I am doing the solution, but just wanted to emphasize those two really three big things. And I'll say it again, relative speed is not new. These three things, what do they mean? And then, of course, the big thing then is it doesn't matter which one you call the primed system and which one you call the unprimed system. All right, so with that, let's actually do number 24. And 24 is colored as a black problem, and I think purposely because they already set up which is the prime and the unprimed system. And so there's not a whole lot of heavy lifting in this problem here. So they have a nice little pitcher, and they put the earth here, and they put an S, meaning this is the unprimed system. Looks like they have a Klingon ship. I'll just make a simple spaceship and put a K here for Klingon spaceship, and they call that the primed system. And so they make the object being the Enterprise. Okay? And so I'll follow their lead, but I'm going to say it again. It doesn't really matter which one you call the prime system, the unprimed system, and the object. So this problem could also be done where the prime system is the Enterprise, and so the moving object is the Klingon ship. It could also be done where the unprimed system is the Enterprise, and so the moving object is the Earth, and then we have our two reference frames. And also we could switch the S and the S prime system here, or if we had them here, they could be switched. And so there's all those, what is that, 6 combinations, different ways of writing this out. And they all will lead to the same answers. So that's the good thing. I don't have to be too particular about which one I call the prime system, the unprimed system, and the object. Just pick one and base everything on that, and then these equations work. Okay? All right, so let me read this problem. It says a Klingon spaceship is moving away from the Earth at a speed of 0.6. All right, so in this reference frame, that would be my V. Remember, what is V? V is the velocity of the prime system as seen from the unprimed system. And the way they label it, that would be the velocity of the Klingon ship. So the Klingon ship moves away from the Earth at 0.8 c. Okay? And again, using there, we could switch it. I want to emphasize that it would still work. Might be a fun exercise to do that. But using their reference, that would be the velocity v. Okay, now we go on. The spaceship Enterprise pursues it at a speed of 0.9 c relative to the Earth. Okay, so the speed of the object as seen from the unprimed system. That's the U. And that's the meaning of the U. The U is the speed of the object as seen from the unprimed system. Okay? Observers on the Earth measure the Enterprise to be overtaking the Klingon ship with a relative speed of 0.1 c. Now, I don't know if that's really important. That's just the difference between them, 0.1 c. See, each of these speeds are from this unprimed system. See, v is the speed by the Klingon ship from the unprimed system, and u is the speed of the object from the unprimed system. So they're not giving us any new information here. They're just saying, hey, this is the closing gap, point C. The real part of this problem, it says, with what speed is the Enterprise overtaking the Klingon craft as measured by the crew in the Enterprise? Okay. And so what we're saying here is the speed between these two, the Klingon ship and the Enterprise, as seen by the Enterprise. Now, if there's anything that's hard about that, is to realize that U prime is really what we're looking for. And the definition of U prime is the speed of the object as seen by this. So really this is a question of what is the speed of the Enterprise as seen from the people in the Klingon ship, is how you would kind of phrase that. But that is the same in reverse as what is the speed of the closing, or how we're closing the gap as seen by the Enterprise. So these two see each other at the same speed. Well, one, I guess, you might call negative. This one is gaining on the Klingon ship, and so it's a positive speed. But if you were in this ship, you would kind of see the Klingon ship getting closer to you. You might call that it's coming towards you at a negative speed. But either way, this is what they're looking for. And so this is where I said I would use this one right here. So u prime is equal to u minus v over 1 minus uv over c squared. All right, so the difference between them, so 0.9c minus 0.8c, which, by the way, is that 0.1c. So that's what we would get without length contraction and time dilation. But then we need to divide it by 1 minus, and so this would be the 0.9c, and this would be the 0.8c all over c squared. Makes the math kind of easy because this would be 1 minus, and all the c's would cancel off. And of course, 9 times 8 is 72. And so 72 with a decimal there. And so grabbing a calculator and doing the 1 minus the 0.72, I get 0.28, and so this is 0.1c over 0.28. And so finishing that, 0.1 divided by 0.28 gives me 0.357c. So not a whole lot of math. I don't think that's the hard part of this. Really, it's understanding the relativity. And I tried to go back to understand, where we have these relativity and what these symbols mean. And there's the answer. Hopefully that helps. Bye now.